Okay. Okay. So, hi, I am Arindam Mullik and you all are welcome to my channel Technical Ori, Live with Programming. And I like to welcoming you in this my live class. So in this video, we are discussing on the AVL tree data structure. What is the reason behind this new tree? That means AVL tree coming. What is the behind? What is the reason behind the coming of the AVL? Then we are discussing on the procedure of creating the AVL tree. Then we are discussing like which there is a different types of rotation. What are the different types of rotation? We are discussing. So let's start with me. Now, first of all, before going on the concept of AVL, first of all, we try to again we are discussing on the BST in my previous video, but here also we are trying to generating BST, create a BST. Okay. Now, what is the reason behind of the creating BST? Why you require? I will explain after some time. But for now, just follow. Now, so here we take some keys elements, that is 30, 41, 11, 50, 25, and 33. And with the help of these key elements, we are generating our binary search tree. So, okay, so try to generate. Okay, try to generate. So first element, that is 30. So 30 become the root. Now, next element is 41. So what is the 41 place? The which place 41 is inserted? Okay, 41 is greater than 30. That means go to the right child. Yes. So inserted 41. Now, next element is 11. Oh, okay, 11 is smaller than 30. So become 11 become the left child of the 30. Next element is 50. So what is the position of 50 become, or where the 50 is inserted? Okay, 50 is greater than 41. Also 50 is greater than 40. 50 is greater than 30. Same way 50 is also greater than 41. So 50 is become the right child of 41. Now next is 20. So where the 20 inserted? Okay, 20 is greater, 20 is less than 30, but 20 is greater than 11. So 20 become the right child of 11. Next is 5. For the 5, if we inserted, 5 is okay smaller than 30. Same way 5 also smaller than 11. So 5 become the left child of 11. Next element 33. What the 33 inserted? Okay, we check first. Okay, 33 is greater than 41 but less than 33. That means less than 41. So 33 become the left child of 41. So we have successfully inserted all the elements in our binary search tree. We have created our first BST. Okay. Now, if I ask a question, tell me what is the height of this binary search tree? Like, how can I calculate the height? What is the process? Take the longest path, or you can say maximum edges. Take the maximum edges. We are not counting the nodes here. We are just counting the maximum edges or longest path. How can I calculate like this on this path? On this, we can choose also this path. That means this, or this, or this, or this. So if you have counted the edges 1, 2, or in this path 1, 2, in this path 1, 2, or 1, 2. That means every time if you take the longest path, how many edges are there? 2 edges. So what is the maximum edges? 2. That means height is also 2. So what is the height of this binary search tree? 2. Now we are do some changes. Here, what we do? Remaining the same elements, remaining the same key elements, but here on this we are take the same key elements but arrange these keys on the different order. Why you do that? I will explain after some time. Why we are just take the same key elements but of the different order, arrange the key elements of the different orders. What is the reason? I will explain after some time. But for now, just follow. Okay. So this is the key elements, like we are arranged like 50, 20, 41, 30, 11, 33 and 5. Okay, making the binary search tree with the help of this keys. Okay, let's start. So 50 become the root. Now where the 20 goes, next element is 20. What the 20 placed? Okay, if 20 is smaller than 50, 20 become the left child of 50. What is the next element? 41. Okay, 41 is lesser than 50 but greater than 20. So 41 become the right child of 20. Okay, next element is 30. Okay, 30 is lesser than 50. Go to the left subtree, but greater than 20. Go to the right child of 20. That means right subtree of 20, but smaller than 41. So 30 is become the left child of 41. Next element is 11. So where the 11 is inserted. Okay, if you are check, 11 is smaller than 50. Also 11 is smaller than 20. So 20 become the left child of 20. That means 11 become the left child of 20. Next is 33. What the 33 place? Where do I insert 33? Okay, 33 is become the 33 is smaller than 50. Okay, but greater than 20 become the right subtree. Again 33 is smaller than 41, become the again left subtree, but greater than 30. So 33 is become the right child of this 30. Next element, last element, that is 5. Where the 5 are inserted. Now we check. Now first of all, 5 is smaller than 50. Go to the left child. And again 5 is also smaller than 20. Go to the again left child of 20. Again 5 is smaller than 11. So 5 is go to the left child of 11. So this is our binary search tree with the help of these key elements. Now if I ask a question again, tell me what is the height of this binary search tree? Height means longest path, or you can say me, sir, height means the maximum edges. How can you calculate the path, longest path? This is the one path, like this, or you can say this, or you can say this. If you take this path, what is the how many edges are there? 1, 2, 3. If you take this path, how many edges are there? Okay, for this to this, 1, 2, 3, 4. That means 4. This is 3, this is 4. Take the always maximum. That means 4. Take the 4. What is the height? So height is 4. That means the height of this binary search tree is 2 and the height of this binary search tree is 4. Now again we arrange these key elements of the different order. Take the another order. Arrange these same key elements, take the different order. So here we take the different order, like 50, 41, 33, 30, 20, 11, 5. Now again we try to make the BST. Okay, 50 is become the root. Okay, what the 41 goes, next element is 41. What the 41 place? Okay, 41 is smaller than 50. Go to the left child of 50. Next element is 33. Okay, 33 is smaller than 50. Again 33 is also smaller than 41. 33 become the left child. 30, next is 30. Okay, 30 is smaller than 50. 30 also smaller than 41. 30 also smaller than 33. That means 30 become the left child of 33. Next is 20. Okay, 20 is smaller than 50. 20 also smaller than 41. 20 also smaller than 33. Again 20 is also smaller than 30. So 20 become the left child of 30. Next is 11. Next is 11. The 11 is again smaller than 50. 11 also smaller than 41. Go to the left part. Left is left subtree. 11 also smaller than 33. Go to the left subtree of 33. Again 11 is also smaller than 30. Go to the left subtree of 30. Again 11 is also smaller than 20. Go to the left subtree. That here, this is the place of 11. Right, left child of 20. Last element, that is 5. Last element, that is 5. If you check, the 5 is smaller than 50. Also 5 is smaller than 51. Smaller 5 is smaller than 33. 5 is also smaller than 30. 5 is smaller than 20. Again 5 is smaller than 11 also. So 5 become the left child of 11. Now, so this is our binary search tree we make using these key elements. This is using these key elements. Now if I again ask a question, what is the height of this BST? If you check like 1, 2, 3, 4, 5, 6, height is 6. Oh, That means for the same key elements, if you arrange the same key elements of the different order, that means we get the how many tree? For the three different order of the same key elements, we generate the three different binary search tree. Three different binary search tree. And also the three different height. First binary search tree, if you take this order of the key elements, we get the height is 2. And if we are get this order, we are getting the height is 4 of this BST. And same way, if you take the this order and is the key elements this order, we get the height is 6. That means now our target is that why we take the different orders of the same key elements. Our target is that we are just try to check if there any effect if we take the different orders of the same key elements on their height of the BST. Yes, it is affected. Here we also see that we are not getting just three different BST for the different orders, but also the different height. Height is also changes. Height is 2, height is 4, and height is 6. Now, what is the reason why you use the BST? Searching and nodes. Searching and nodes. Binary search tree. We are basically searching the nodes. Now, here, if I ask a question, okay, tell me how many comparison are required if you are searching the node that is 5 on these three binary search tree. Now, okay, first of all, we check for the first binary search tree. If I ask you, tell me how many comparisons are required for the searching the node that is 5. So, okay, let's start with the first binary search. Check with the first binary search tree. First comparison here. Okay, 5 is smaller. Go to the 11. Go to the left child of 30. Compare with 11. Again, 5 is smaller than 11. So go to the left child. Again, compare with 5. That means 1, 2, 3. That means 3 comparisons are done here on this first BST of height is 2. Again, for the same procedure we have done in the second binary search tree. Here also we are find out the how many comparisons are required for searching the key element, searching the node that is 5 on this binary search tree. How many comparisons? We check. Okay, first comparison, then go to the left child, second comparison with 20, third comparison, then fourth comparison. That means, oh, 4 comparisons are required here. If the height is 4, that means 4 comparisons are required here. And so we are observed that if the height is 2, that means there is a 3 comparison. If the height is increases, we also our comparisons, number of comparisons for searching a node also increases. Now again we check. Take this order. Okay. Now same procedure we have follow here. We are again searching the 5 and try to find out the how many comparisons are required. Okay. First comparison, then second comparison, third comparison, fourth comparison, fifth comparison, sixth comparison, and seventh comparison. That means if the height is 6, we require a 7 comparisons. So why we are basically find out on these diagrams, on these trees? That means if our height is increases, also on that time for that cause our searching time, that means number of comparison for finding an element in the binary search tree is also increases. Here we find that what is the height of this binary search tree? 2. We are required the 3 comparison. Now what is the height of this binary search tree? 4. That means if our height is increases from 2 to 4, we are required a 4 comparison for finding this, searching this 5. Again, if we are, what is the height of this binary search tree? 6. So 4 to 6, our height is increases from 4 to 6. How many comparisons? 7 comparisons are required. Okay, that means try to say that if the height of the binary search tree is also increases, that means we require the lots of comparison. That means our searching time is so greater. That means so large. There is a big problem. This is also drawback of the binary search tree. That means if the binary search tree, if we are taking the different orders of the same key elements, height is also affected. Height is also changes. If the height is also greater, that means height is large. That means we have take the lots of time for searching an elements, or we can say number of comparison for searching an element is also increases. This is a drawback of the binary search tree. This is a drawback of the BST. In BST, if we changes the order, that means elements on keys, that means we are get the different BST of the different height. Again, it is also generate the problem of the number of comparison. Now, if I ask a question, which you are preferred? A binary search tree having the lots of like lot height, that means higher height, and the search time is greater, or you are preferred the a binary search tree having the less height, that means our number of comparison or searching time is less. Obviously, you prefer the second. A binary search tree having the less height, or you can say the searching time is less. Obviously, we choose the second. That means every time we are performing a way that is easier. That means what is easier case here? Here easier case here is found an element, found a node on the easy way, or that means less time. The time, or we can say number of comparison is less. So now in this tree, which you are chooses, obviously you choose the first. Why? Because here is there is only 3 comparison and height is 2, but here 4 comparison, height is 4. Here again 6 7 comparisons. Oh, lots of comparisons are there. That means lots of time taken for searching an element. So we are preferred this. That means we are preferred thus a binary search tree having the less height. That means why we are choose the a binary search tree of the less height? Because every time we try to find out the binary, that means a search element, that means a key, on the less time, now less number of comparison. So we are choose this rather than these two, rather than this second and third. We are choose the first option. Now, so that means what I try to say that, so with the same key elements, we can also generate a tree, a binary search tree having the larger height, or we generate a binary search tree having the less height. Both we are performed, but we are choose the second option. That means we are generate a binary search tree having the less height. Now again, this is just an example. Okay, here you also take some keys. Here we also take some keys like 31, 21, 15. We have to take the another example. This is the same thing as we will already show here, but here also we take the another example here. That's why it is a more clear up to you. What is I try to say? Why you take the reason for taking this BST? Again we take. Okay, here is a 3 key elements here. Generate the BST. This is a BST. How can I generate it? I will not explain here because already I will explain how can I generate the BST. Procedure of generating BST. So here we are not explain what is the process of generating BST. Now this is the BST I created. What is the height? 1, 2. Height is 2. Again, take the different order, arrange these key elements with the different order here, and again generate the BST. This is the BST we have generated. What is the height? Again 2. Again, take the same key elements with the different order, generate the BST. Generate the BST. What is the height? 2. Now again, take the same key elements with the different order, in this order. Arrange the key elements with this order. Generate the BST. We are generate the BST. What is the height? 1. Oh, that means here also we found height is also changes. Here is 2, here is 2, but here is 1. Here is also 1. That means now, is there any possibility, that means generate this for the same key elements, is there any possibility for generating the lots of trees or lots of shapes? Yes, there is a possibility. Yes, there is a possibility. For the different orders, we are also see that we generate that for the same key elements, taking with the different order, we are also getting the different trees. For the 4 different orders, we are generate the 4 different trees. Or we can say for the same key elements with using the taking or arrange the same key elements with the 4 different order, we are getting the 4 shapes, 4 different shapes. Yes, we are get the 4 different shapes. But is there any other shape for the, like, is there any another arrangement? We are getting the another or more trees. Yes, there is a possibility. For different order, we get the different tree or different shapes. But my question is, how many trees are possible for these three key elements? Is there any another possibility? Here we are taking the four orders, so we are getting the four shape. But is there any another possibility? That means if you are get the another more shapes rather than four, yes, there is a possibility. What is the formula? There is a formula. If there is a n elements, we are getting the n factorial number of trees, or we can say if we are having the n elements, we are getting the n factorial number of shapes. So how many elements are there? 3 for now. So we get the 3 factorial, that means 6 shapes. That means we get the for the these 3 key elements for the generating the different order, we are get the 6 shapes. 6 shapes. This is the formula. Now 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 I have a question. So so we found that our target is, what is our target actually? Our target is generating the lot height, that means larger height binary search tree to lesser height binary search tree, right? For the reduce the searching time, or reduce the number of comparison for searching an element. How can we do that? What is a procedure? There is a procedure called rotation procedure. What is the meaning of actual rotation? How many rotations are there? I will explain after some time. Okay, I will explain after some time. But for now, just taking it as a simple way. Okay, taking it as a simple way. Just try to understand. Try to understand. We'll explain after this rotation details. Okay, try to understand. For an example, what is our target actually? What is the height of this tree? 2. Height of this tree 2. Height of this tree 2. Height of this tree 2. What is the height of this tree? 1. Is there any we take the another elements? No, but the order we are taking the 1, 2, 3, 4, 5. 5 different orders for the same same key elements. We are taking arrange the same key elements with the 5 different orders or 5 arrangements. But we are getting the 5 different tree. But among the 5 different trees, this tree having the less height is 1. But on the other 4 is height is 2. So we are generate every tree are converted with this tree. That means to every tree we are transformed with this tree. That means to this tree. This tree is converted with this. This tree is converted with this. This tree is converted with this. This tree is transformed with this to this. Okay. Now, how can we do that? We are do the procedures called rotation. How can we do that? For an example, just think about that. We are here. There is a nail and there is a thread. There is a thread. We are just pull this. Okay. If I ask a question in a simple way, for an example, you just forget about the rotation procedure. If I ask a question, how can you making from this tree to this tree? What you answer? The answer is that, sir, first of all, we take that 21 here, 21 on the upward, and 31 become the right subtree, and 15 become the same. Okay. Now, yes, it is right answer. You are do that. You are tell the right answer. Here also in the rotation procedure, we are do the same thing. We are do the same. We are also do the same thing here, but on the different way. But on the different way. Now, how can I do that? How can we do that? Now, for an example, how can I do that? With the help of rotation. What is the actual rotation? I will explain after some time. Now, I have a question. For an example, we have a this tree, and I say, please convert this tree to this tree. How can I do that? What is the procedure? What is the procedure of the like converting with the this second tree to this tree? What is the procedure? What is the procedure behind the converting of this second tree to this fifth tree? You just forget about the rotation, forget about this rotation process. Do the simple answer. So okay, you are if you are observed here 21 was the upper part, so Okay, 15 is go to the pull 15 here, 21 is the upper, and 31 be the same place. That means 31 is the take place of 21. Here also we do the same thing. Okay, 15 is pull here, 21 is the upward, 21 has become upward, pull here, 15 here, 31 become the same. Yes, this is a procedure. Forget about the rotation for this time. I will explain now what is rotation actually after some time. But for now, just simple way. You just think about the simple way for generating this tree to this tree. Simple way. Now, if I ask a question, okay, say me, how can you generate from this tree to this tree? What is the answer? Okay, if we are see like this 21 is on the upper side, okay. Okay, first of all, we have do that like 21 was the upper, 21 become the top, so 21 be the top, and 31, okay, 31 become the pull 31 here, 21 become the top, and 15 is remaining same. We are also do same thing here. Forget about this rotation. What is the rotation procedure again? Yes, you are right, we are do generating the what transform this tree to this tree, this tree to this tree using the rotation procedure. But for now, just you are thinking about the simple way. Forget about the rotation, the complex thing. I will explain what is the rotation in the easy way after some time. Now, here it is a three, like three. Okay, three nodes are there. Okay, again. Now, if I ask a question, okay, transform from this tree to this tree. How can I do that? If I observed, okay, 21 in the root, okay, fine. So 15, we are pull 15 here, 21 become the root, and 31 remaining same. Yes, we are do the actual do there. Same. Yes, we have performed with the help of rotation. Without help of rotation, it is not possible for generating this tree on like this tree to this tree or transform with this tree to this tree. No, it is not possible. But for now, I think it is clear up to you. How can I pull the thing? Like for an example, if you're now you are, I like to touch what is a rotation procedure. For an example, if I tell you that please generate this second tree to this tree, what is a procedure? For an example, there is a nail. We have fixed here a nail, and this is like a thread. We have pull this thread. So 15 is become this side, 21 become the upper part, and 31 that takes place of the 21. So this is the way. Or we can say here also, if there is a nail fixed on 31, there is a thread. We have pull with the thread. So 31 is come here, 21 was become the upper part, 15 is go to the place of 21. We are generate this. Or if I ask a question here, if I ask a question, generate the from this tree to this tree, what is the procedure? Again, this is a two-step here. For an example, first of all, a nail is fixed here. We are assume that is a nail is fixed here on the 31. We are just pull. There is a thread. There is a thread. Okay, pull the thread here. Pull the thread on this side. Okay, so 31 is come here. 21 become the upper part. So 31 become the right side of the 21. Again there is a pull, there is a nail here, we are fixed on the 15, there is a thread. Okay, pull here. So okay, so 21 like go to the upper part, 21 become the upper part, and 15 is pull, we are 15 is go there, 31 remaining same. Then we are this tree are generated. This is the short procedure of the rotation. What is the actual procedure? I will explain after some time with the help of some example. Now, as I think it is up to clear that what is the concept of the rotation. Just I like to hear the touch of the rotation. What is the actual procedure? I will explain after some time. Now, rotation are done only the three nodes at a time. Keep in mind, we have done the rotation only with the help of three nodes. That means in every time you have done the rotation with the helping the three nodes at a time. Now, so this is the concept. That means the converting with the this tree to this tree, converting this tree to this tree, or converting this tree to this tree, this tree to this tree with the help of this rotation. This is the concept of coming the AVL tree. Now we are discussing on what is AVL tree. Now we are discussing on the about the AVL tree. What is the AVL tree we are discussing? First of all, we know that who generated, that means who are invented the AVL tree. Why we are this meaning of this AVL? This is a basically nothing but the name of the inventors. The name of the inventors of the AVL tree is Mr. Adelson, Velsky and Landis. With the first letter of the inventor's name, A, Adelson, we are taking the A. From Velsky, we are taking the V. And from Landis, we are taking the L. Taking this AVL, we are generate the AVL. We are named as this tree AVL because the name, by using the name of the inventors of AVL tree concept. Now, next point. AVL tree is a height balance binary search tree. What is the meaning of the height balance? I will explain after some time. But for now, just keep in mind, AVL tree is a height balance binary search tree. That no doubt, AVL tree is a binary search tree. No doubt. Yes, AVL tree is a binary search tree. Simple BST. But height is balanced. What is the meaning of height balance? I will explain after some time. Now, go to the third part. For every node, we are calculate the balance factor. For the every node, we must calculate the balance factor. What is the balance factor and how can we calculate actually? I will explain after some time with the help of some example. But for now, just remind that. Now, how can you calculate the balance factor? What is the formula for generating or calculating the balance factor? The formula is for calculate the balance factor is height of the left subtree minus height of the right subtree. Again, I repeat, for calculating the balance factor for every node, the formula says that formula is height of the left subtree minus height of the right subtree. Or you can say in short, BF, that means balance factor, is equals to HL minus HR. That means height of the left subtree minus height of the right subtree. And balance factor of the every node should become the -1, 1 or 0. That means every time, keep in mind, every time you just keep in mind, balance factor every time must be belong on this 3. That means balance factor only possible just 3 value. What is the 3 value of the balance factor? 1, -1, 0. Other than this 3 value, balance factor is not possible. Balance factor must be this 3 value, 1, -1, 0. So I think it is just introduction part of the AVL tree. I think these points are clear up to you. Okay. So go to the next part. Now we are discussing on the rotations in the AVL tree. I think you are understand what is the concept of the AVL tree. What is the meaning of AVL tree? What is the reason behind the coming of AVL tree? Now, how many rotations are there? I will already explain that there is a rotations on that. This is the concept of AVL tree with the help of rotation. How many rotations are possible in AVL tree? 4 types of rotations are possible. First, LL rotation. What is the meaning of LL? I will explain after some time. Now, second is RR rotation. What is the meaning of RR? I will explain after some time. Third, LR rotation. What is the meaning of LR? I will explain after some time. And fourth is RL rotation. RL. What is the meaning of this LL, RR, LR or RL? How can we perform these rotations? I will explain after some time as our video are progressed. But for now, just remind these 4 types of rotations are possible in AVL tree. LL rotation, RR rotation, LR rotation, RL. Again, I repeat, LL, RR, LR, RL. Now, next is now we try to explain what is the balance factor and how can you calculate for a node the balance factor. First of all, what is the formula? Again, you write the formula here also. Balance factor means height of the left subtree minus height of the right subtree. Or we can say BF equals to HL minus HR. Or balance factor must be the 3 value, -1, 0 or 1. Oh, okay. Now check again. For this BST, If I ask you, what is the balance factor of this node? Is there any child of this node? No. That means, what is the height of left subtree, right subtree? 0, 0. Both are 0. That means 0 minus 0, 0. For this tree, for this node, if I ask you, please calculate the balance factor, what is the answer? Is there any child node? No. That means, what is the height of left subtree? 0. What is the height of right subtree? 0. Again 0. 0 minus 0, 0. Now, for this node, we are calculating. What is the height? How many edges on left subtree? 1. How many edges on right subtree? 1. That means 1 minus 1, 0. Yes. Is there any belong? Is these values that belong on this 3 part? That means 3 values. Under these 3 values? Yes. All are become the 0. Yes. Is on the this limit. This limit. Now, again we are calculate the balance factor for the every node of this BST. That means this tree. Now I give you a short note about the balance factor. Every time you must keep in mind, if you are calculate the balance factor for the leaf node, means have not any child, not calculate, just put on the 0. Why? If you are check here, is there any child? No. That means, what is the height of left subtree for this leaf node? 0. What is the height of the right subtree? 0. That means 0 minus 0, 0. So you just comment that if there is a leaf node and you are calculate the balance factor for the any leaf node, you just put the 0. Every time keep in mind, the leaf node, the balance factor of the every leaf node of a tree must be 0. Now here, for this node, we are calculate what is the height of the left subtree? 0. What is the height of the right subtree? How many edges? 1. 0 minus 1, that is minus 1. Again, calculate the balance factor for this node. Calculate the balance factor for this node. If you are calculated, what is the balance? What is the height of the left subtree? 0. That means there is a no child for this node. But now, what is the, if I ask a question, what is the height of the right subtree? How many edges are there? We are just calculate the edges, not the node. 1, 2. That means 0, 0 minus 2, 0 minus 2, minus 2. Now, is the minus 2 is belong on this limit? That means on the 3 value? No. That means it is imbalance. If the balance factor is become this limit, balance factor value is become this under this limit, that means minus 1, 0 or 1, it is a balance. Otherwise, it is imbalance. So yes, this node is imbalance for the value of minus 2. Calculate the balance factor for this node. Calculate the balance factor for this node. What is the height of the left subtree? 1, 2, 3. So 3. Height of the left subtree is 3. What is the height of the right subtree? 1. Only 1 edges. That means 3 minus 1. 2. Again, it is imbalance. Why? 2 is not this belong this limit. That means belong, not belong. 2 is not belong with this 3 value. So yes, this node is imbalanced. This node is also imbalanced. Now, again, this is a leaf node. What is the balance factor? I already told you. If there is a leaf node, you just comment that every leaf node having the balance factor is 0. So we are just put here 0. So I think now it is clear up to you that you are familiar with the how can we calculate the balance factor for the every node of the tree. Now we are go to our rotation part. First of all, we are see what is the LL rotation. For that, we are taking the initially if one binary search tree. We are taking this BST. Calculate the balance factor for the every node. What is the balance factor for the 30? This is a leaf node. Well, okay, so what is the balance factor of 30? 0. And we know that if there is a leaf node, we are calculate the balance factor. Obviously, balance factor is 0. Now, calculate the balance factor for the 50. How many? Now, what is the formula? Height of the left subtree minus height of the right subtree. How many edges on the left side? 1. How many edges of the right side? 0. That means 1 minus 0. Balance factor is 1. Is this tree is balanced? Yes, because this node's balance factor is 0. This node balance factor is 1. That means all node are be the on this limit of the balance factor. Yes, so that whole tree are balanced. If any node is imbalanced, that means tree is also imbalanced. If any node of the binary search tree are imbalanced, that means whole tree are also imbalanced. Now, so this tree is a balanced. Now we are do some modification. Insert a node that is 20, insert a 20. Okay, where the 20 go? 20, okay, 20 is become the left. 20 is smaller than 50. Go to the left subtree. Again, 20 is smaller than 30 also. So 20 become the left child of 30. Now, check the balance factor. What is the balance factor of 20? 0. What is the balance factor of 30? 1 minus 0, that is 1. What is the balance factor of 50? Okay, 1, 2. 2. And what is the height of the right subtree? Is there any nodes? No. Is there any edges? No. That means 2 minus 0. 2. Now, yes. Again, it is imbalanced. That means this 50, this node, is become imbalanced. Why? What is the value of balance factor? 2. Is this 2 is belong on this 3 value? No. So yes, rule says that if our balance factor value is not, it's under this limit, this become the imbalanced. So this is the imbalance. Now we know it is an imbalance, but why it is imbalanced? What is the reason behind the imbalance? Because we are insert an element left of 50. That means left of 50. We are inserted the 20. That is the reason 50 is imbalance. Left of left. Now, if I ask a question, what that means? Yes, we found that 50 is imbalance because we are inserted an element of the left of 50. That means we are inserted this 20 or left of 50. But what type of imbalance is this? Left of left. That means LL. We can say it is a left imbalance. Left imbalance. Further, inserting a node in the left of 50, we are inserted 20. That's why this tree is imbalance. So it is, we can say it is a LL imbalance. Now, for generating now, that means these three are not balanced. For balancing, we know that, or you already know, for balancing, we require the rotation. So which rotation we are performed? LL rotation, RR rotation, LR or RL rotation? Now, here, every time keep in mind, the name of the rotation and name of the imbalance must be same. That means, for the LL imbalance, we are must do the LL rotation. That means for the L, if there is a, you found there is a LL imbalance, you just comment, we are must do our LL rotation. How can you perform the LL rotation? Now we are observed that. Tell me which node is imbalance? 50 is imbalance. 50 is imbalance. Okay. Now pull up. Okay. So there is a pin. For an example, you just find there is a pin we are fixed here. Okay. There is a nail we are fixed here. Now this is a thread. And we are pull on with the help of this nail. That means if you are pull the thread on this side, so 50 is pulled here, 30 become the upward, 20 is on the place of 30. That means what I try to say, that if you are pull this thread on this part, on this side, 50 is go there, pull on this side, 30 is become upward, and 20 is go to the place of 30. So obviously this tree is generated. This type of tree are generated. Why? If you have pull 50 here, okay, 50 is come here, 30 is on the upward, 30 is become upward, and 20 is remaining same. So this is the after performing the LL imbalance, or we can say after performing the LL rotation. For why? For remove this LL imbalance, we are performing the LL rotation. How can you do that? Just simple. Assume that there is a nail and there is a thread. We are just pull this thread on this part. In this side, we are pull. So obviously 50 is come here, 30 is go to the upward, and 20 is remaining same. That's why I generate this type of tree. This is the after LL rotation, we get this binary search tree. Now, if I ask a question, is this tree is balanced? Here I not write a balance factor. Why? Because you are just calculated. You examine is this is a balanced tree or not. How can you examine the tree is balanced or not? Check the every node of the balance factor. How can we check? If I ask a question, what is the balance factor for 20 and 50? Is a leap node. So 20 balance factor is 0. For 50 balance factor is again 0 because what is a leap node? Now check the 30. What is the left height of left subtree? 1 edges. Right subtree 1 edges. That means 1 minus 1, that is 0. It is again 0. So yes, this is a all nodes are belong, all nodes balance factor is belong on the these values. So yes, this is a balanced, this is a balanced BST. So we are successfully do our LL rotation. Next, again, now we are talking about the RR rotation, right rotation. Now, so for that we are taking the BST, taking a BST. This is a BST we are taking. Okay. Now, if I tell you, please calculate the balance factor for these two nodes. What is the balance factor of 60? Leaf node, obviously balance factor is 0. If I calculate for the 55, 0 minus 1, that is minus 1, yes, it is balanced. So the whole tree is balanced. Now we do some modification. Insert 65. What does 65 goes? 65 is greater than 55 as well as 65 is greater than 60. That means 65 is inserted on the right side of 60. Now we check the what is the balance factor of the every node. What is the balance factor for the 65? 0. What is the balance factor for the 60? Okay, there is a no. Okay, if I check the left subtree, there is a no node. That means 0. What is the, how many edges on the right subtree? What is the height of the right subtree? How many edges? 1. That means 0 minus 1 minus 1. Check the balance factor for the 55. Left subtree, no node. 0. 0 minus 2, that is minus 2. Okay, right? Now that means minus 2. Oh, that means this node is imbalanced. We have crossed the value of the minus 1, 1 and 0. Here we are getting the minus 2. That means this node is become imbalanced. Now, why? Now, question is that why this 55 become the imbalanced node? What is the reason? Because we are inserted the 65 on the right of 55. Right of 55 we insert this 65. That's why this tree become imbalanced, or we can say 55 is an imbalanced node, or this tree is become imbalanced. Which type of imbalance is this? Right, because we are insert this 65 on the right of 55. That's why it is the imbalance name is RR imbalance, or this is a RR imbalance. Now which type of rotation we are perform? LL, RR, LR or RL? What is the name convention says? Name convention says that the name of the imbalance and name of the rotation must be same. That means for remove this RR imbalance, we have must be perform the RR rotation, right rotation. How can we perform? Now we are check. Which node is imbalanced? 55 is imbalanced. Pull a nail here. Now there is a thread. Okay. So pull this thread on this part. Pull this thread on this side. So 55 is come here, 55 is come on this side, 60 goes up, 60 goes up, 65 on the place of 60. That means after the other rotation, we are generating this tree. From this tree, after do the other rotation, we are generating this tree. Again, I repeat the procedure. There is a nail, or I assume that there is a nail and this is a thread. We are pull this thread using this nail on this side. We are pull this thread. That means 55 is goes on this side, 60 is become up, 65 is go to the place of 60. So 60 is goes up, 55 we are pulled here, that means left child of 60. 65 is goes here on the place of 60. That means we are generating 65 will become the right child of 60. So yes, after RR rotation, we are generating this tree. This is the RR rotation. Now examine the balance factor for the every node. Balance factor 0. Balance factor 0. What is the balance factor of 60? 1 minus 1. 0. Again 0. Yes, it is this. All nodes are balanced. That means this tree is balanced tree. Next is LR rotation. So we take this. Initially, we take this binary search tree. Now calculate the balance factor. Balance factor is 0. Balance factor for 32, 1 minus 0, that is 1. Modify this trees in a little bit. Insert 15. So from where what is the place that 15 is inserted? Okay, 15 is lesser than 32 but greater than 11. So 15 is become the right child of 11. Calculate the balance factor for each node. What is the balance factor for 15? 0. What is the balance factor for 11? 0 minus 1 minus 1. Balance factor for 32. Okay, 1, 2. And that is 0. That means 2 minus 0. 2. Yes, okay. That means the this node is become imbalanced. Oh, why? Why this 32 is become imbalanced? Why? Because what is the value of the balance factor here for this node? 2. Okay, 2 is the 2 is belong on this limit -1, 0 and 1. No, that means yes, this is an imbalance. So this tree become the imbalance. This is an imbalance node. Now, which type of imbalance is this? Now, what is the reason behind the 32 is become imbalanced? Because we are insert a node 15 on the left top right of 15, left top right of 32. We are inserting this 15 of the left of right of 32. So that's why is 32 become the imbalance. Which type of imbalance is this? Left top right. That means left right imbalance. Left right imbalance. For removing the LR imbalance, we are must using the LR rotation. Why? Name as the name says that LR imbalance. So obviously, for remove the LR imbalance, we must perform the LR rotation. LR rotation for balancing this tree. Now we see how can we perform the LR rotation. So I just copy this tree on here. Now keep in mind, this as the name says LR, that means two letters are there. That means we are do the two-step rotation, or we can say we can do the double rotation. Two-step rotations we are performed. First step, first of all in LR rotation, put a nail here, put a nail on the 11 here, and this is a thread. This is assume there is a thread. Rotate the 11 on this side. That means 11 is come here, 11 is come here, 15 is goes up. This become a this tree. That means 15 is on the up, 11 is on the left part of the 15. That means left child of 15. First rotation is over. Again, second step. This tree is generated. Second step rotation. Pull a nail on this 32. There is a thread is coming here. Pull the thread on this part. That means 32. Okay, 32 is come here. 32 is go this side. 15 is on the upward. 11 is remaining same. So after the LR rotation, we are generating this tree. How? First of all, on this rotation, 15 is go there, go upward. 11 is come on the left part of 15. Yes, this tree is generated. Second rotation, that means second step of rotation. Pull a nail here. There is a thread. We are pull this thread on this part. 32 is go there. 15 is on the upward. 15 is upward. 32 is go there, and 11 is remaining same. That means 11 is become the 15 is on the become a root. After go to the upward of the 15. Now 11 be remaining same. That means 11 be the left child of 15. 32 is come this side. That means 32 is become the right child of 15. So our LR rotation is completed. So after LR rotation, this tree is generated. This BST is generated. Keep in mind, LR rotation, here we have performed the two-step rotation, not two rotation. We cannot say we are do that two rotations. No. Rotations we are every time LR is a single rotation. Treat as a single rotation on LR. But yes, there is a two-step rotation. This is the first step rotation, and this is the second step rotation. So we can say LR is a double rotation. LR is a double rotation, or is a two-step rotation. So I think LR is clear up to you. Last, now can we do? So now if you observe, there is a two-step rotation. This is a complex thing. Because this is a complex thing. Here is a just 3 node. Maybe there is a lots of nodes, or take the lots of time, because we have to take the two-step. Can we do the LR rotation single step on as LR on RR? Yes, we do that. How can you do that? There is a simple way for do the LR rotation on the single step. What is the rule? Rule says that, okay, bring the last node on the root. Bring the last node on root. That means 15 is become the root. That root node, previous root node, was go to the right child of the coming node of the root. That means here 15 is coming on the root. That means 32 is become the right child, and left child is remaining same. Left child is remaining same. That means 11 become the left child. This is a one step. How can I do that? Again, I'll explain. Okay, just keep in mind on the simple way. Just bring the 15 here on the root. Bring the 15 here. 32 is go there. 32 is go there. That means 32 is become the right child of 15. 11 is remaining same. So 11 is the left child of 15. That is a simple step. One step procedure to the LR rotation. You can also perform the one step of LR. Otherwise, you have do the, if you are there is a problem, you also prefer the two step. You have do the two step rotation for the LR. You can also do that. If you are, what is a your choice? Your choice. If you are do the one step rotation, it is also okay. In the one step, you are also do that in the simple way. This is a simple way. Or you otherwise you choose this two step. You are first of all you are rotate this type on this way, this side, and then it is a become this tree, then rotate this part, that means rotate this side. You also, but tree is same. You are do this two step rotation or one step rotation, tree is also same. Your choice, up to your choice. Now last rotation, RL, right left rotation. This is the last rotation of the AVL. We are taking the one BST here. Now check the balance factor. What is the balance factor of 30? 0. What is the balance factor of 11? 0 minus 1 minus 1. Now we are just little bit modified of this tree. Insert a node that is 21. What the 21 insert? Okay, 21 is greater than 11 but less than 30. So 21 has become the left child of 30. Calculate the balance factor. What is the balance factor for 21? 0. What is the balance factor for 30? 0, 1 minus 0, that is 1. What is the balance factor for 11? 0 minus 1, 2. 0 minus 2, that is minus 2. Oh, here is the value are coming, balance factor, that is minus 2. That means this node is becoming imbalanced. This 11 is node is becoming imbalanced. Now, what is the reason behind why this 11 is becoming balanced? Because we are inserting a node of the right of left of 11. Right of left of 11, we are inserting a node that is 21. So that's why this 11 is become imbalanced. Now, which type of imbalance is this? Right of left. That means right left imbalance. Right left imbalance. So the reason is for imbalance, this imbalance of this 11, the whole tree is become an unbalanced tree or imbalanced tree. This type of imbalance we are saying right left imbalance. Now for removing the RL imbalance, which type of rotation we are performing? Name convention says that rotation name and imbalance name must be same. That means we are use the, for removing the RL imbalance, we use the RL rotation. RL rotation. Okay. Now, how can you do that? How can you do that? Perform the RL rotation. Check here. Copy this tree here. Now, again, RL is also a two-step rotation. As a same of LR rotation, here on LR we also say that is a two-step rotation, or we can say LR is a double rotation. Here RL also a double rotation or two-step rotation. Here also we do the rotation on the two-step. First of all, pull a nail here on the 30 and there is a thread. There is a thread. Now pull the thread on this side. So 30 is come here. 21 is become the upward, so 21 is go to the root, 30 is become the right child. Okay, so this type of tree is generated. This type of tree is generated. Again, do the rotation on this side. Pull a nail here on the 11 and there is a thread. Pull this thread on this side. So 11 is come here. 21 is become the upward, go to the upward. 30 is go to the place of 21. So after do the RL rotation, we are get this tree, this BST. Again, I simple way I understand. I try to understand you. Okay, this is a for an example on this rotation. I think it is clear up to you. How can I perform? 21 is go up, 30 is go to the right child of 21, and here there is a for an assume that there is a nail or pulled a nail here. This is a like a thread, and in this direction we have pulled this thread. So 11 is come here, 21 go to the upward direction, 30 is go to the place of 21. So after this this is the RL. So obviously, if the 11 is come here, so 11 is go to the left side. 21 go to the upward. That means 21 become the root. 30 is go to the place of 21. Yes, 30 is come here. That means 11 is become the left child of 21, and 30 is become the right child of 21. So this is the our generating. This is the binary search tree, balanced binary search tree after the RL rotation is performed. Again, now we again check the what is the balance factor. Is this tree is balanced? How can we check? Check the balance factor for the each node. 0, 0, 1 minus 1, again 0. Yes, this tree is balanced because all nodes are balanced. Again, this is a double rotation. Same as LR, RA also a double rotation. Or we can say RL is a two-step rotation. Here, first step is this and second step is this. And the same way, as per the RL, here also we try to do this two step on the one step. We are rotating the RL rotation, perform the RL rotation on the single step. How can you do that? Same way, here, okay, the last node is bring the root. Last node is bring the root. So 21 become the root here. 30 is remaining same. 30 is remaining same. And 11 is go there. 11 is go there. That means 11 is become the left child of 21. This is a simple way, one step. On one step, you are performing the RL rotation. Now, this is up to your choice. If you are try to choose this way, that means two step, you also do that. Or otherwise, if you are try to do this RL rotation on a single step, you also do that. This is up to you which type of step you are perform. If you are you are do that on the two step, is there any problem? You must choose the two step. First step is rotate this part, and then choose. Then on the next step, you are rotate on this part, and we generate three are also same. It is up to you which type of process you are choose, two step process or one step process. This is a simple way because it is just do a simple one step process and are generating the same tree after LR rotation. Sorry, RL rotation. Now we are on the last step of this video. Here we are now at last we are try to generating a AVL tree with the some given keys. Generate AVL tree, and here our target is that we must perform the rotations here for balanced this BST. Okay, let's start. First of all, 45. Okay, take the 45. Okay, so 45 become the root now. First, initially, check the balance factor. That means we are insert a node and making the BST, and every time we check the balance factor. If it is a balanced, no problem, it's a balanced tree. Otherwise, if any node on the BST with making with these keys elements, if any node is unbalanced, make the balance with the concept of rotation. This is a procedure for making a AVL tree. In short. Okay, go forward. So first of all, insert 45. Check the balance factor. Only one node. Balance factor is 0. Next element 22. Okay, 22. So what the 22 inserted? 22 become the 22 is lesser than 45. So 22 is inserted on the left side. That means left child of 45. Okay. Next. Now again, if you are check, now we are check. What is the procedure? You are making insert one by one node on the BST binary search tree, making a binary search tree, but every time keep in mind you must calculate the balance factor. You must calculate the balance factor for the every node. Now check the balance factor for the 22. What is the balance factor? Leaf node, balance factor is 0. What is the balance factor of 45? Only one node is a left child. That means one edges. 1 minus 0, that means 1. Yes, it is this tree is balanced. Next element, insert 15. 15 is go to the left of 45. That means 15 is smaller than 45. Same way, 15 is smaller than 22. 15 is become the left child of 22. Now, check the balance factor. 0, 1 minus 0, 1. 2 minus 0, 2. Yes, this 45 is become imbalanced. Which type of imbalance? LL imbalanced. Because left of left we are insert a node. Which type of, so we are performing the rotation for remove this LL imbalance. Which type of rotation? LL. How can you perform the LL rotation? On which node? On the basis of which node? Which node is imbalanced? 45 is imbalanced. On the basis of the 45, we are do the LL rotation. Pull a nail here. There is a thread on this side. Thread, pull the thread here on this part. So what is the procedure of LL rotation? I already show you what is the procedure of LL rotation. Just we are performed. Pull this 45 here. 22 is on up. 15 is remaining same. That means 22 is go to the upward. 22 is become the root. 45 is come on this side. 45 is become the right child of 22. And 15 is go to the place of 22. So 15 is become the left child. So after LL rotation, we are got this tree. Check the balance factor. 0, 0, 1 minus 1, 0. Yes, this is a balance tree now. Insert 23. Insert 23 now. Okay, where the 23 inserted? Okay, 23 is greater than 22, but less than 45. So 23 is a left child of 45. Check the balance factor. 0, 0, 1 minus 0, 1. 0, here, 1 minus 2. Yes, minus 1. Balanced. These trees are balanced. Insert 31. Insert 31. 31 is greater than 22, but less than 45. But again, 31 is greater than 23. So 31 will become the right child of 23. Check the balance factor. 0, 0 minus 1, minus 1. Acha, now check the balance factor for the 45. 1, 2. That means 2 minus 0, 2. Oh, this is the imbalanced. First of all, the rule says that, but if you had say, sir, if you calculate the balance factor of the 22, how can you calculate? 1 minus 1, 2, 3, minus 2. No, no. Before calculating the balance factor, you must fix this imbalance part of this tree. Now, but if you are counted on the here, you find that this 22 is imbalanced. Now, which type of imbalance? Right, left, right. That means R, L, R. No, you are not take the 3 step. You just take the 2 step. R, L. From anywhere you are inserted. That means you are inserted the 31 here or here. No. Here or here. But the rule says that here you only take the 2 step. Now you ask a question, sir, in the which step we are taking? Is this we take like 22, 45 and 23, or we take 45, 23, 31? Here we take the 45, this tree, this subtree. Why we are not taking this 22, 45, 23? This is also imbalanced. Reason is that first of all, this tree is making, that means this is the first part. First of all, we fix the imbalance, this part, then we are fixed here. That's why, that means first of all, we see the imbalance, this node become imbalanced, but and we are cross on the upper way. No, first of all, we fix the imbalance part of this node. That means this subtree for this node 45. First of all, fix the imbalance part of the 45. Then we are go to the 25. That means 22. Okay. So which type of rotation we are performing? LR rotation. We are performing the LR rotation. Now, how can you perform the LR rotation? Here also, what is the step? 2-step process. 2-step process. How can you do that? First of all, balance this part. That means pull a nail here on the 23. This is a thread. Pull this thread on this part. That means 32 is go to the upward, 23 is go to the left part. Yes. After the converting, after the rotation, this rotation is completed. This tree is this type of subtree are making. Again, rotate on this side on the basis of 45. There is a nail and this is a thread. Pull this thread on this side. 45 is come here, 31 is go to the upward, 23 is remaining same. That means 45 is come here, 31 is upward. That means 31 become the root now. 23 is remaining same. Yes, remaining same. 45 is go to this side. That means 45 is become the right subtree. That means right child of 31. Check the balance factor here. So after LR rotation, we get this tree. This is the LR rotation. It's a two-step process. I think it is clear. I already told about the LR rotation, how we perform. After LR, we have got this tree. Check the LR rotation. Check this tree, the balance factor of the every node of this binary search tree. 0, 0, 0, 1 minus 1, again 0, 1 minus 2, minus 1, minus 1. Yes, this is a balanced. Next. Now we are inserted the next element, that is 29. 29 were inserted. Okay, where the 29 are inserted? Okay, 29 is greater than 22, but smaller than 31. Go to the left part, but greater than 23. So 29 become the right child of 23. Check the balance factor. 0, 0 minus 1, minus 1. Okay, here 0, 0, 2 minus 1, minus 1, 2 minus 1, 1, 1 minus 1, 2, 3, 1 minus 3, minus 2. Oh, 22 is become imbalance. Which type of imbalance? For which node we are these are imbalanced? 29. That means R, L, R. No, it is not a R, L, R. We only take the two step. We only take the two step. What is the two step we are perform? What is the two step we are perform? This is the RL. This is the RL. Okay, so this is the RL we are perform. This is the RL we are performed. So RL. Now you are asking me a question, sir. From the where we are take this RL, right left, always start from the node which are imbalanced. Always start from the node. That means here we are starting from this RL. Always take these three node. Every time we are, I already told on the time of rotations, every time we take the three nodes at a time. So we are taking these three node. Not execute, include this node. Every time you take the three node from the starting from the which node is imbalanced, we are taking the another two nodes. So this node is become imbalanced, and which direction? Right, left. This node. That means these three nodes. Perform the RL rotation on these three nodes. How can you do that? Now here we take the one step process on the single step. What is the process on the RL? Last element, bring the last element on the root. So 23 become the root. 31 is remaining same, and 23 is, and now 20 now so 23 is become the root. What is the process? This is a simple one step process of the RL. This one step process we are applied here. What is the process says? Last element, bring the last element on the root. Bring the last element on the root. 21 be the root. 30 is remaining same, and 11 being the left child. Same way here also we do the same thing. 23 being the 23 on the root, 23 on the root, 31 remaining same, and 22 is become the left child of 23. 22 become the left child of 23. 15 is remaining same. That means 15 is be the left child of 22. Now what about the 29 and 45? 45 is remaining same. That means right child of 31. Right child of 31. Now what is the position? What is the position of the 29? What is the now on the previous, what is the position of the 29? 29 was become the right child of the 23. Same way here also 29 become the right subtree. Right subtree. Now we are check the, how can I do that? Right subtree. That means 29 in the after the RL rotation, 29 become the right subtree of the 23. So okay, so the up to this we are performed. What the 29 go on right subtree? Okay, 29 is greater than 23. So go to the right side, but less than 31. So 29 is inserted on the left subtree of the or left child of 31. So this is after RL rotation, this tree is generated. This tree is generated. Now last element we are inserted now 52. So where the 52 go? 52 is greater than 23, also greater than 31, also greater than 45. So 52 is become the right child of 45. 52 is go to the right child of 45. Again, check the balance factor. 0, 0, 0, 0, 1 minus 0, 1, 0, 1 minus 2, minus 1, 2 minus 1, 2, 3, 2 minus 3, minus 1. Yes, these all nodes are balanced. So yes, after inserting all the nodes, means all the elements, this has become our binary search tree, and these all elements having the balanced. That means we can say it is a balanced binary search tree. So yes, this is a AVL. This is our resultant AVL tree. So I think now it is clear up to you what is the AVL, how can we generate the AVL, what is the reason behind the AVL tree. I think it is clear up to you, and I have tried my best for understand this AVL tree concept. I think it is clear. Thanks for watching these live classes, and please supporting me. And this type of more videos you are getting on the next futures also. Thanks for watching.